So for those just now joining on the recording, thank you. This is the September 2021 meeting of the Astronomy Fundamentals Special Interest Group. Tonight we have two presentations, getting close to continuing our march towards completing all the constellations. David Evans will be presenting the Southern constellation Hydra. Hydrus, excuse me, thank you. Not to be confused with the Northern constellation Hydra, which I just did. Slip of the tongue. And after that, I will be presenting our main topic on the astronomer William Herschel. So that was actually a really interesting presentation for me to put together. So I hope you'll enjoy that. And with that, David, I need to make you a co-host so that you can actually present.
All right. You gave me a great segue. You'll see that on my second slide. I'll share.
You should now have permissions to screen share. Go ahead and give it a shot.
All right.
And while you're doing that, I forgot to send out my bod report this month. I apologize. I'll have to slip that in next month. It slipped my mind completely and I didn't see any email notification, so I apologize.
Okay, we'll look forward to getting it next month. Thank you.
Actually, I'll probably just send out this month's and last month's right after this meeting on the weekend. So I
Okay, super.
So I can focus on class instead of waiting.
Super.
All right. Can everybody see my slide?
Yeah.
Yes.
All right. So constellation Hydrus for this month. So Hydrus does not equal Hydra. Thanks for the segue, Connor. Hydrus is the male water snake, and Hydra is the female water snake. And there's quite a contrast between the two. Hydra is the largest of the 88 constellations, measuring 1,303 square degrees. And being a snake, it's the longest of all the constellations at over 100 degrees in length. Hydrus, on the other hand, often known as the lesser snake, is the 61st largest constellation in spanning 243 square degrees. Hydra straddles the celestial equator and was first described in the 2nd century by Ptolemy. Hydrus was too far south to be observed by the ancient Greeks and was first described by Planicus in 1597. As you recall, Planicus described 12 constellations in the far south. So Hydrus, the diagram shows 3 stars. It has a regular shape, and it's bordered by Mensa to the southeast, Uranus to the east, Horoglygium and Reptilium to the northeast, Phoenix to the north, Tucana to the west, west-northwest, Noctans to the south. It has a declination of minus 5785 to minus 82. So it's not visible from locations north of plus 30. The French astronomer Nicolas Louis Decail, which is on the upper right, modified Hydrus from Planicus's original drawing, while Decail was observing from the Cape of Good Hope in South Africa in 1756. He actually made Hydrus a little bit smaller in his map of the region.
Real quick interjection. From past topics, I believe it's pronounced Lakai, and the L's are silent.
Great, thank you, appreciate that.
Typical French with all of their silent characters like Messier and their silent R's and silent L's.
And you know, I flunked French in high school, so.
I've had 4 years of French between high school and college, so it's one of those you just never forget.
It also got a little bit of notoriety because in Moby Dick, Herman Melville mentions both Hydrus and Argonavis, highlighting his knowledge of the constellations in southern whaling regions. So Hydrus again was established by Planicus, and it had originally 15 stars. Connor, how do we say Lacaille?
Lacaille.
Lacaille, I'm sorry, modified the constellation to include 20 stars in 1756, but he actually made it smaller. 5 of the stars in the Hydrus constellation have identified exoplanets. However, it has no Messier objects and only faint deep sky objects. But it is very near to the large Magellanic Cloud in Dorado, which on this map is on the left side, and the small Magellanic Cloud in Tucana, which is the green circle on the right. And the small cloud actually gets into the region of Hydrus, and we'll talk about that later. So again, usually the alpha star is the brightest, but in this case, it's the beta. It's the closest bright star to the South Pole, and Beta Hydrae shines at magnitude 2.8, and it's 24 light years from Earth. It has a mass of 104% of the sun and a radius of 181% of the sun. It's 3 times more luminous and has a spectral classification of G24, a subgiant star. Its classification indicates that it's exhausting its hydrogen fuel at its core, giving us a glimpse of our sun's future state. And there's one possible Jupiter-sized exoplanet out there, but as of the last report that I saw, it's not confirmed. But that report was several years ago, so it may have been confirmed since. Alpha Hydrae is at the top of the triangle. It's a white subgiant star of mag 2.9, and it's located 72 light years from Earth. It's easily found that that large black dot just north is Achenar, which is the 9th brightest star in the sky, and it's located in the constellation of Uranus. Alpha Hydrae is a F04, and it's in the very late stages of burning hydrogen in its core. It's 2 times as massive as its sun, and it's 3.3 times its radius, and it shines with a luminosity of 26 times of our sun. But it's interesting, it's almost done burning hydrogen, but yet it's a very young star at 810 million years old. So burn bright and die fast. Gamma Hydrae forms the left lower triangle. It's the 3rd brightest star in Hydrus, and it shines at magnitude 3.24. It's 214 light years from Earth. Its spectral class is M23. It's a red giant star. It is 60 times the sun's solar radius and 655 times more luminous. It's interesting because Gamma Hydrae is a semi-variable pulsating star, which varies between mag 3.26 and 3.33. However, they haven't established its period as of yet, so the star warrants more study. The next star is actually very, very close to Gamma Hydrae. It's just 3 degrees northeast. It's not on the map of the star chart that I have here, but the middle of the circle is about where it's at. And it's called VW Hydrae, and it's a dwarf nova of the SU Ursae Majoris type. And variables of this type are composed of a compact binary pair with a solar type secondary star, while the primary star is a white dwarf star. And then there's an accretion disk around the primary component. So the observed outbursts are believed to be the result of interactions within the disk that circles the white dwarf. And this can be sometimes very extreme. You can have your normal dwarf nova outburst, which consists of a rise from normal to 2 to 6 magnitudes over a 1 to 3 day period. And then occasionally these stars display bouts of super outbursts, which are even brighter. So this star gets a lot of attention for that particular reason. So let's take a look at some double stars. Phi Hydra is a red giant, and it's on the left-hand side with I think, a black circle around it. It's 476 light years distance, and Phi Hydra 2 is an orange giant at 488 light years. It's not a true binary system, but really just an optical double. Eta Hydra, on the other hand, is also a optical double. The first star is a blue-white main sequence star located 700 light years from Earth. And Eta Hydra 2 is a yellow giant located 218 light years from Earth. And they have found an exoplanet around Eta Hydra 2 of 6.5 Jupiter's mass. And that's an orbit around Eta Hydra 2. A couple other stars that have exoplanets. HD 1080 is a sun-like star. It has 7 and possibly 9 exoplanets. It's 127 light years from Earth and shines at a magnitude of 7.33. Either at 7 or 9 exoplanets in one system, it's one of the larger number of systems known in terms of number of exoplanets. So it does get a lot of study for that. The next is GJ3021, another sun-like star, 57 light years away. And it has another Jupiter-sized exoplanet orbiting very close at 0.5 AUs, and it has a period of 133 days. There is also a true binary star with GJ3021, which is a companion red dwarf, but that red dwarf is orbits out at 68 AU. So there's a lot of questions about how that orbital system works. It appears, from what I understood, is that the Jupiter-sized exoplanet orbits just 3021, while the binary dwarf actually orbits them both and is probably independent of any activity going on with the exoplanet. HD 2003 or 20003 is a magnitude of 8.7. It's a yellow main sequence star of the type G85. It's a little cooler and smaller than our sun, and it's 143 light years away. It has 2 planets that are around, and these are rocky planets. They're around 12 and 13.5 times as massive as the Earth, and their periods are 12 and 34 days respectively. So at least in my mind, a rocky planet that large, especially that close in, I think we'll hear a lot more about this particular system. So that's it for the stars in the system. Most of the other ones are either nondescript or not named. Matter of fact, none of the stars in that system are actually named like Betelgeuse or Achenar. So they're all just named by their catalogs. So deep sky objects, IC 1717. This was originally found by the Danish astronomer John Dreyer in the late 1800s, very near the Eta Hydra binary system. However, it's no longer there. Some speculate that it was a supernova, but this is discounted because if it was a supernova, it would have severely affected the Eta Hydra system. They're very, very close to each other. So it was more commonly believed that it's a faint comet that's moved on. But either way, there's nothing there anymore. I just find it interesting that they still keep the designation when nothing's there. The picture on the right is the White Rose Galaxy, and this is PGC 6240. It's 345 million light years from Earth, and this is likely the result of two galaxies who have collided in the past. The galaxy, when you look at it, has many young 400 million year old clusters juxtaposed with many of the much older clusters that are 1 billion years old and more. So really the thought is, and this is also a elliptical galaxy, that it's really the result of an ancient collision sometime in the past. Another one is NGC 1511, and this is a spiral galaxy located just north of Gamma Hydra and south of Beta Reticuli. Its magnitude 11.3 and it's 62 million light years distance. While it's not visible from Tucson, observers farther south will be able to view it in amateur class telescopes. And I found a lot of literature on this one, in particular, a article, and I have the source at the end, by Corey Balaski and Manthe, who suggest in their paper that NGC 1511 is really two galaxies. It has a companion galaxy of 1511b, which is not in this picture, but the galaxy has been severely disturbed. In fact, both have been severely disturbed by the collision. And in their paper, they suggest that the group displays a prime example of interaction induced star formation, or star formation is caused by collision between two different objects. And it was a pretty interesting, I frankly understood very little about the paper except for the abstract, but it was an interesting read. NGC 602 is actually, it's a bright cluster on the edge of the small Magellanic Cloud, and it's embedded in the N90 Nebula. And the N90 Nebula is essentially the brightly colored spots or gas around the edge of that. NGC 602 is actually three different groupings. The first grouping is that large central grouping just south of, or just to the south of the center part. The other one is on the far left, and then just the two bright stars really just above the middle of that photo is the third grouping. So these three groupings of NGC 602 have pushed away that less dense gas and formed what they call elephant trunks of that nebula. And I think that's a pretty good description of what they look like. And around that, you have very high star formation. And most of the star formation, and this is in the Hubble Space Telescope, most of that star formation is unseen. You'd have to take the infrared and the Spitzer Space Telescope to really see that star formation. You don't see it in this picture, but there's a lot of it's going on, and it's all being generated by the solar winds, compacting the gas around the elevator, around the elephant trunks from the three components of NGC 602. And that picture is from the Hubble. Another one in NGC 1466. We leave the small Magellanic Cloud and we go to the large one. This is in Hydrus, but it's probably more associated with Tucana, or with Dorado, excuse me. NGC 1466 is noted for having 49 and possibly 50 RR Lyra stars. Now, RR Lyra variables are periodic variable stars, and they're often found in globular clusters like NGC 1466. And the neat thing about our Lyra stars is they're used for standard candles to measure extragalactic distances. And a lot of this work was done by the female astronomers at Harvard. And I imagine, Doug, you'll cover this quite a bit next week. But I read a comment that if we did not understand our Lyra variables that the women at Harvard studied, our understanding of the galaxy formation in the universe would be dramatically different. So our Lyra variables are typically metal poor population stars, and they're confined on a very narrow region of the Hertzsprung-Russell diagram. And it's interesting, their pulsations, or what makes them variable, is driven by radiation that's partially blocked from escaping the star. As the radiation is trying to escape, and it can't, you get an increase in pressure and temperature, which makes them expand. But while they're expanding, gravity takes over again and contracts them, and you get variation based on that. And it turns into a very regular variation that makes them such great stellar candles. So that's it. Not a lot in this in Hydrus. A very small and dim constellation far south. But what there is very interesting. So my sources, most of this information came from Wikipedia, but also Constellation Guide. And a lot of the very interesting information came out of the AAVSO, along with other sources, the Hubble Space Telescope, the Carnegie Irving Galaxy Survey, Telescopius, and then that paper which I referred to by Manthe and Korbolowski was Neutral Hydrogen Gas and Interacting Galaxies, the NGC 1511 Galaxy Group. So those are the primary sources I've used. Any questions? No questions? Connor, I guess I'll let it back to you.
Thanks, David.
Yeah, thank you.
Let me get my desktop in order here. Too many PDFs open for school at the same time. Cool. And is anyone able to see my screen?
Yes.
Awesome. So moving right along, tonight we're talking about the astronomer William Herschel, who has a lot of things credited to his name. And so some of them that were very much ahead of his time. So when my keyboard decides to work and I can hit next slide. Come on. There we go. So William Herschel was born in Hanover, Germany in 1738 to his father Isaac and mother Anna. He was one of 10 children amongst his parents, including his younger sister Carolyn Herschel, which we will probably learn more about next month. William, his father, and his brother Jacob all served as oboists in one of the many knight groups that were common in Europe at the time in the early 1700s. Keeping in mind that at this time, Germany was then known as the Holy Roman Empire with a lot of independent city-states, which all kind of hated each other. So at this time, the Hanover Duchy, I think it was a duchy, was allied with the English crown, and they, despite being a territory of the Holy Roman Empire, highlighting there's a lot of complex political relationships during this particular period in history. The Hanover Guards were sent to England, which is the Hanover Guards, which was the guard group that the Herschels were, the three Herschels were members of, were ordered to England in 1755 until they were recalled back to England in 1757 to defend the city against a potential war with France. Hanover, that being an ally of England, it made the sense to have them as a target of any potential conflict. During one such battle, the Hanover Guards were defeated. This is known as the Battle of Hastenback. And Will's father sent his two sons back to England to seek refuge after the battle. At this point, it's known that William's brother Jacob had received a discharge from the Knight group, but William was never given a formal discharge, so he was actually later accused of desertion. And it took some of his later works where he became acquainted with King George III, who then pardoned him from this crime just because it was something that was never documented. His brain fart. What was his discharge? I don't know why that escaped me. Since the 1700s were commonly referred to as a great boon for classical music, you had a lot of really great composers during this time. And so music featured heavily in Herschel's early education. Again, he was an oboist inside of a military band. So he was acquired proficiency over many of his early years with several instruments, including the violin, harpsichord, and the organ. Primarily playing the latter three as part of normal church services in England after he moved there after the Battle of Hastenback. He actually has 24 symphonies credited to his name and a lot of other small minor musical pieces, which is kind of impressive that he managed to write that many symphonies, which are usually large, 10, 20-minute pieces of music. During this time, after his migration to England, he became the head of the Durham militia band for a year or so. And he served as the first organist of what is now Halifax Minster Church in England. Eventually, he ended his musical career when he was appointed the director of the Bath Orchestra in 1780, where he often used his sister Caroline as part of the soprano role in various operas. Before finishing up the tour, before we get into some of his more important astronomy exploits, he was married in 1788 to Mary Pitt in Slough, England, where they were living at the time, and where Herschel maintained his observatory. The first and only child between the couple, John Herschel, was born in 1792 when William was at the age of 54. So kind of pretty late for having a child by today's standards. I forgot to include the age of Mary Pitt in this, so I don't actually have that off the top of my head, so I apologize. He was elected as a foreign honorary member of the American Academy for Arts in 1788. And I put this here because it was kind of interesting that at this point, America was, as a country was barely going on, 3 or 4 years old. I think we had just adopted the Constitution in 1788. So it was it's one of those things where just like, he was given this honor to a country that at the time really wasn't significant, which it gets kind of one of those like, that's funny. Especially so when considering that at the time John was considered an Englishman, and so you have kind of the bitter relationships of the American Revolutionary War here. Kind of like an odd thing to have happen. He eventually died in Slough, England on August 25th in 1822. So his first exposure to astronomy was through a book called A Complete System of Optics by English mathematician Robert Smith. Smith was one of several thinkers at the time who was working to promote the works of Isaac Newton. So this book was a complementary to that. He came across Smith because Smith had also published a book on acoustics. So he was actually driven into astronomy through the channel of music, which at the time was also very related to mathematics. So he, jumped straight from music all the way into astronomy. As part of reading the book, he acquired an interest in building his own telescopes. And over the course of several years, he would grind the primary mirrors for his own reflector telescopes, sometimes spending as much as 16 hours a day. And eventually his sister Caroline, when she moved over to England from Hanover, would become very important in his role, in the construction of many of the telescopes that Herschel used. This is an example of one of the mirror polishers that he uses. This is currently on display in the William Herschel Museum in England, which is currently at the site of his old house. His observational history as a professional astronomer, which at the time he wasn't a professional astronomer yet, was focusing on binary stars. Using his own 6-inch Newtonian telescope, he began observing career like many of us do from the back of his house in England. Being the mid 1700s, at this point, there's really no light pollution in England, so he don't have to worry much about that there. He presented his findings on many of the star systems that he observed to the Royal Astronomical Society between 1780 and 1783. I cannot. Most of his observations. Excuse me, I'm jumping ahead of myself. So he would continue to publish double star observations for better part of a decade, well into the time when he had actually begun working on assembling the general catalog, which would eventually become the NGC catalog, which we talked about last month. He was the first person to propose and then confirm that some binary systems are what we now know as orbiting binary stars. They weren't optical binaries, where they're just two stars that are on the optical binaries, or two stars that are on the same line of sight but don't orbit each other. So he was the first one to connect that some of these star systems are actually true multiple star systems. They aren't solo stars like our sun. And his works here on double stars actually set the basis, a lot of the foundational work that led into, that is used in modern day binary star astronomy. So he, one of several fields that he helped spark and help build out, which we now is a very active area of research today. His next major achievement was the discovery of the planet Uranus. During an observational run in 1781, William was observing, I think it was in the constellation Hydra, a fuzzy disk as part of his observational campaigns, where he was documenting some. He first believed the fuzzy spot to be a comet, and if anyone who has seen a Uranus through one of their own telescopes is kind of as an interesting take, but considering the optics at the time, it does make sense. We just a small pale blue dot for Uranus. And he wanted to resolve more details about it, trying to see what type of comet it was and looking through various things. He reported the findings to English astronomer Neville Maskelyne and Russian mathematician, Anders Johann Lexell. Neville, his claim to fame as being the first person to actually to empirically measure the mass of the Earth. Interesting topic on him if you want to go learn more about that. Lexel and William, they set out collaborating and trying to compute the orbit of this comet that Herschel had found, and eventually settled on an agreement that it was likely a planetary object that was beyond the, and it was certainly beyond the orbit of Saturn. So having this potential new planet in hand and setting out to try to help establish himself a wealthy patron, he named his new planet Gregorium Sidus after King George III, which proved to be a pretty smart play on his part. But bitter relations between France and England meant that they actually didn't call the planet Gregorium Sidus in France, and they actually just called it the planet Herschel after the Increditors, after the discoverer's name. His discovery of the planet earned him English knighthood and a position as a court astronomer, which eventually earned him a pardon for his desertion, as we talked about earlier, and also set him up to be with a steady paying job, which he used to formally abandon his musical career and allowed him to pursue astronomy full time. He would later discover the two moons of Uranus, Titania and Oberon, in 1787. At some point between his discovery of Uranus and his double stars campaign, someone had sent him a copy of Messier's famous catalog, piquing his interest in deep sky objects. And from 1782 to 1802, using at least he used at least 4 different telescopes in his observational efforts to catalog various deep sky objects, which formed the foundation of what we now know as the General Catalog and the NGC Catalog. Using two telescopes that each had a 20-foot focal length, one telescope with a 7-foot focal length, which is the telescope that he himself built. One of the first telescopes that, one of the first telescopes that he built himself, and it was actually one of his personal favorite telescopes. And the large monster, which known as the Great 40 Telescope, which remained the largest telescope in the world for about 50 years during this time period. So this is a rough drawing and sketch of the Great 40 Telescope. It was paid for by money from the English crown. It cost about, in $1,700, about 300 British pounds for all the iron, which is quite a bit of money. But the whole telescope is assembled out of iron. And I have a picture of the primary mirror, which still exists and is housed in a museum at this point. And interesting, even though the British Crown paid for the telescope and continued to pay money for the telescope's maintenance, it was owned outright by the Herschels. Kind of one of those weird things you wouldn't necessarily link together in, usually when the royal family pays for something, they own it. So it was interesting split in ownership. This is the primary mirror of the Great 40 Telescope. You see that it's, I'm not quite sure from this picture if the lack of shine is just from the construction techniques of the day, or if it's just showing off how much the metal has not corroded, has aged, and that we're seeing, I forget the term for it. Anyone remember what the term it is for, like, when you have the anodization or whatever it is, like on silver?
It oxidizes.
Oxidizing. Thank you. I don't know why. Yeah. Or if that's just or if the lack of shine here on the mirror is just because the metal itself is oxidated and aged over time. So this mirror might at one point have been much more reflective than this picture currently indicates. But this mirror is, I think I said 48 inches. So this is about a 1 meter mirror by today's standards. All throughout this time, through his cataloging of deep sky objects, his discovery of Uranus, he would be working with his younger sister Carolyn, who moved to England in 1772 and proceeded to be indoctrinated into astronomy by her brother. She became his official assistant when he was recruited as a court astronomer for the British Royal Court, and would eventually become a qualified astronomer in her own right, making a lot more discoveries, which hopefully we'll learn more about here over some other presentations. But two notable items is that she was the first paid female professional astronomer and the first female in England to be given a government position. Doug, were you trying to speak? I heard some background noise over a mic. I'm not quite sure who it was. Was anyone chiming in there? No. Okay. Kind of talking through their working relationship. When one of the 20-foot telescopes came into service, William was attempting to observe and record all of his observations, which involved this lengthy process of going to the telescope, looking at the sky, running inside, letting his eyes adjust to the candlelight that he was using to write down his observations, writing them down, running outside, waiting for eyes to get dark adapted again, and then repeating the process. But once Caroline settled more into her role, he eventually just started shouting his observations to her as she sat next to a window upstairs in their house and acting as his official scribe, while also relaying any references or other details that he needed, such as objects that might be in an area of the sky that he's currently looking at through a library that they kept in the house. His next major discovery was the discovery of infrared light. He originally, being a builder of his own telescopes, he wanted to find a color of glass that would work as a filter to enable him to view the sun. In the late 1790s, he noted that depending on what material he used, some would allow more light through, but a lot of light through, very little heat, and others would enable the opposite, allowing very little light through, but a lot of heat. Through a series of experiments, this led him down a line of reasoning that one color was best for viewing and another color was best used for heating, potentially as for cooking food or things like that. I would strongly advise, do not try to repeat these experiments today on your own. You will likely damage your eyes because the sun is very bright and can be a dangerous target to look at unless you have proper equipment. So please don't do that. So moving down his chain of experiments as he was setting out to investigate this light, these colors that produce heat, he built what eventually became a precursor to modern spectrometers, called a spectroradiometer. And there's a diagram of this here in a second. I wasn't able to find definitively if he was the original inventor of the spectroradiometer or if he borrowed the idea from someone else. There was some evidence that Newton had something similar, so it's not quite clear if he was the actual inventor of the spectrometer. So in this case, he used one, but I don't know if he was the actual inventor of the item. So in a spectroradiometer, it's really quite a simple.
Oh, it can't be the same one. Sorry.
So in a spectroradiometer, it's divided into a prism, a glass sliding window so that they can use to observe specific colors. Today, this would be a slit that would be used inside of modern spectrometers to separate out specific frequencies of light, such as infrared, that would get cast onto modern sensors. And 2 and 3 thermometers. There's only 2 shown here, but he actually used 3. Well, 1 thermometer was used to record the temperatures of the light channel that he was looking at in his experiments in this particular image, recording the temperature of yellow light. The other 2 were used to serve as control temperatures, control thermometers to record the background temperature of the ambient room. So just really simple: a prism, a sheet of paper, 3 thermometers. Using this, he was able to determine that the temperature, and that depending on what color he was looking, some of those, that the temperature and the brightness change with specific colors, and observed that yellow colors or pale green colors were the visual brightest, which we didn't determine until much later that this is because this is the primary frequency of colors emitted by the, sorry, not the primary frequency colors, the brightest colors that are emitted by the sun, and also ones that our eyes have biologically evolved to be more sensitive to. He saw in the, as he was working down to record the various temperature readings of the colors over many months, he noticed that there is this interesting line on his beta as he was graphing it, that although red had the highest temperature, there was no plateau, like you would expect with a curve to go up, like a wave curve, which would go up, it would peak and then start going down. And it actually, his beta just kept going beyond where red was. Writing at the time, I likewise conclude that the full red falls short of the maximum heat, which perhaps lies even beyond a little bit of visual refraction. Here, he's basically saying that what we conclude is that, hey, there's the heat keeps going up even at beyond the areas of red that I can see with my eyes, and concluded. And concluded that there were some types of light that emitted by the sun, which were unfit for vision, essentially saying, hey, there's this unseen type of light that we just don't observe, kind of, which was interesting for a lot of reasons, which I will fail to explain in this just because there's a huge article, and I will point out the reference if you want to go read more about some of the conclusions and how it was reached. So over the course of 200 different experiments, I apologize for the typo there, he eventually concluded that heat and light both came from the same source. Well, the same phenomenon, excuse me. Some of his other key discoveries is he was the first to propose a model of the Milky Way galaxy through observational data, correctly assuming that it was in the shape of a disk, but he got a lot of other details wrong. For one, he assumed that the sun was at the center of this disk and not something else, which he, as kind of mentioned a couple of times, he assembled the general catalog, which would later become the NGC catalog, which was published by his son, John Herschel. He discovered 2 Saturnian moons, Mimas and Enceladus, and he was one of 2 astronomers that observed that the Martian ice caps grew and shrank depending on the season on Mars. He was also the first to determine what direction our solar system is moving in the galaxy. Currently, we are moving in the direction of a region of space in the constellation Hercules. And he was only off by about 10 degrees in that original and of what we now know today is the true direction. So considering error bars at the time, that's actually a phenomenally precise estimate. And he also helped found the Astronomical Society of London, which would later become the Royal Astronomical Society, which has those two groups playing a very large role in some of the discoveries for modern astronomy over the last 200 years. This is a rough picture of Herschel's model of the Milky Way. Kind of, you can see here on the sides, you have the spiral shape on this plane here. Let me see if I can laser pointer. Here we go. But other than that, there's not a lot of details that we would recognize today from, what we've seen from both visually and of what the Milky Way looks like. But still, this is a phenomenal effort to just catalog and position all of these stars. Questions or comments? I'll have references up here in a second after this slide.
I always thought Herschel was older than 1780s or something like that. I thought he was like in the 1600s or whatever, or 1500s. But okay.
Surprise! He certainly was one of the astronomers that came after Messier, since many of his objects in the NUC catalog incorporated objects from Messier. So kind of. But yes,
Okay.
Yeah, I think it's so amazing that he was a musician, all that music that he did. And that he's such a totally well-rounded person.
Person of note.
So if you actually want to learn a little bit more about, if you like reading about some scientific history, this link here at the bottom has a really good story and really basic, really informative on describing the process about how Herschel discovered and defended himself in his discovery for infrared light. He was actually it was actually a very controversial discovery. Some of the people who were experts in light and heat actually were attacking him because they thought that an astronomer didn't have a place in the field and that he didn't know what he was talking about. So it was actually a little bit more of a rough and tumble adventure in his, as he published his work on infrared light. It was also really interesting to see how he reached from one conclusion to another to just say, no, this thing is real. So this is actually a very interesting read, and I highly recommend it. So with that, that's all I got. Thank you, everyone. If there's no more questions. And ending
Thank
the
you,
recording.
Connor.